So what we're looking at today is the idea of binding energy across the board for all elements, and we'll be making generalizations using graphs and patterns. We'll also be looking at how to find binding energy for more complex situations, when you have a whole atom and a mass of a certain atom, for example. Now, the stability of the nucleus does actually depend on its size. A larger atomic nucleus will have a greater binding energy. However, the stability of an atomic nuclei is determined by the binding energy per nucleon. Now, this is an important difference. Binding energy per nucleon is the binding energy in total divided by the number of nucleons. So, if we have the binding energy of helium-4, the binding energy per nucleon would be found by dividing its binding energy, its total binding energy, which is 28.6 megaevolts, divided by 4, which is the number of nucleons, which gives you a binding energy per nucleon of 7.15. Nitrogen, we can find its binding energy by dividing its total binding energy, 101 megaevolts, divided by 14, the number of nucleons, to give you 7.22 megaevolts. Now, the rule is the more binding energy per nucleon needed, the more stable the nucleus. A really simple way of thinking about this is if we build an analogy of binding energy being similar to glue. Nitrogen has more glue per nucleon than helium-4, and so therefore is more closely bound together, so it's more stable. At this point, I will revisit the definition of binding energy because it's an important definition. Binding energy is the energy required to break up a nucleus into its separate nucleons. The most stable nucleus has the largest binding energy per nucleon. And the idea is that if it needs more energy for it to happen, then it's less likely to occur. And that's indeed the reality, moving away from the glue analogy. In nature, things that require a lot of energy are unlikely to happen. So those nucleons which require less, or those combinations of nucleons that require less binding energy, are more likely to break apart or bind together. And we'll have a look at that in a second. Now, this is a binding energy per nucleon graph. And this is a graph that you can construct using the entire periodic table by plotting the number of nucleons for each element on the x-axis. So that would be the mass number, right? The number of protons and neutrons. And then the average binding energy per nucleon on the y-axis. So if we take something like hydrogen, or an isotope of hydrogen in its simplest form, which is 1 proton, you would put 1 on here, and you would find out the binding energy and plot it. Very small nuclei are very unstable. They undergo nuclear fusion to become more stable. So if we go back to this idea that the less energy, the more likely it is to fuse or to undergo fission, then what you've got here are the small nucleons, things like hydrogen, isotopes of hydrogen, because you've got hydrogen, which is 1 proton, but you could have 1 proton, 1 neutron, 1 proton, 2 neutrons, etc. So they would go here, and they have a very low binding energy per nucleon. So therefore, they are likely to fuse. Well, likely. You'd need a ridiculously powerful solar reactor. But at least it will happen. Here we have larger nuclei. Things like lithium, helium. Helium's your next one here. Lithium, carbon, nitrogen. As we increase the number of nucleons, the amount of binding energy increases. And that means that it's less likely to undergo a reaction like fission and fusion. Now, iron is the most stable nucleus. So this is a really, really important feature. Iron is at the top of this curve because iron is the most stable element. And then as we get bigger than that, then we start to go down again. And these become less stable. And yes, now we're on the side of the graph where we approach areas of fission. Larger nuclei are less stable. They undergo nuclear fission this time to become more stable. So, typical question you would get at the IB is to label a graph like this one with uranium, which would be on this side, hydrogen, which would be on here, and iron right at the top, which is the most stable element. And on these two areas, these are important features. Fission of a large nucleus increases the size of the binding energy. So basically, if you've got an element here, it's low on the graph, so it's less stable. What happens is that it breaks apart. So your nucleus, your large nucleus, will break, and then your daughter nuclei, your more stable atoms, will then be on this side of the graph. They'll climb up the graph. And because they're climbing up, they're becoming more stable. Now, this you know from what we did on nuclear reactions in the previous section. So fission causes your atoms to go up the graph to become more stable. And then fusion of small nuclei, you might have your small nuclei here. As they bind together and as fusion happens, they climb up. So hydrogen's down here, not very stable, becomes helium, that goes up here, and it becomes more stable, it's higher, right? So fusion of small nuclei increases the size of binding energy per nucleon and releases energy. Both of these graphs involve a move towards a more stable area and a release of energy. Okay. And as an extra, I haven't come across many questions that involved mass as opposed to atoms. Most of the mass defect questions that you'll come across involve what is the binding energy of one atom of helium or hydrogen, etc. So just in case though, how do we deal with binding energy for a mass of a substance? So for example, a kilogram of hydrogen is used to make helium. How do we deal with that? Well, it's just to remember some basic ideas, because binding energy, as we've already defined, is the energy difference, the binding energy for one atom, right? If you want to find the energy difference of a mole of a substance, then you would multiply that binding energy that you found for one atom by Avogadro's constant, which is 6.02 times 10 to the 23. Right? That will give you the total binding energy for a mole of a radioactive substance. Now, if you then have like basically a question which asks you about a kilogram of a substance or any other mass, then you would take the mass that you're given in the question and you divide it by the molar mass. Now, this is a chemistry thing, and just in case you're not doing chemistry, molar mass is the mass of one mole of a substance. So 12 grams would be the molar mass of carbon-12. So whatever it is, or whatever mass you're given, divide it by the molar mass and then multiply it by Avogadro's constant and then multiply that by the mass defect. Let's have a go at that. So find the binding energy of 1 kilogram of nitrogen-14 if for one atom the value is 1.62 times 10 to the minus 11 and the molar mass is 14 grams. So try and conceptualize this as if you were building an atom, right? You've got one atom gives you 1.62. So find out in 1 mole, right? If you've got 1 mole, what you would do to this value. And then if you know the energy for 1 mole, then find out how many moles there are in 1 kilogram. And here we have our answer, our mass, which is 1 kilogram, divided by 14 grams. Remember to convert this into kilograms. Then you multiply that by Avogadro's constant, and then you multiply that by your binding energy. And you should get a preposterous value, which is 6.966 times 10 to the 14 joules, which at this huge value just goes to show why fusion and fission reactions are so popular for generating energy, which we can then use. But we'll do that. We'll talk about that in topic 8. But it's actually quite interesting to bridge to that idea. These values tend to be enormous. Okay, so that's that for today's lesson.